Anybody have any homework questions?
Nope.
We didn't have any homework.
Yeah.
Anyone want to know why we didn't have any homework? No. Okay, so we're going to a new topic today. That's internal loads in beams.
Versus not beams?
Yes. What is a beam?
Hunk of something?
A what?
A hunk of something?
That's true. You definitely need a hunk of something. A beam is, so it's the way you picture it, it's like a long, relatively slender thing. But the key to why you call it a beam is actually the way it's loaded. It's not the actual thing. So it's a long, slender body. With at least some loads. Okay, this is getting wordy. Not acting along the long axis. Okay, so there have to be some things that are trying to bend this thing for it to be a beam. Okay? Can you picture that? Like a long, slender thing, but if everything's happening straight along the axis, like in a truss, then you don't think of that as a beam. Those aren't beam calculations. If there are things going on that are trying to bend it, then it is. So you have to have, I don't know. So that thing is a beam. But if you had loads just acting along the axis, then it wouldn't be. Okay, internal loads. What's the motivation for internal loads? Really, the answer to that is the external loads don't tell us where something is going to break. So the external loads don't tell us where bodies will break. And when I say break, that can mean a few things depending on what you're looking for. It can be where the deformation gets too big, or it can be where the thing actually separates. And the best way to visualize that is, I might have drawn this picture at the start of the class, but imagine taking like a pencil between your two hands. And bending it. A free body diagram, sort of a simplified one of this pencil, would look something like this. You have upward forces from your thumbs, downward forces from your fingers. And so just based on the external loads, we do statics to calculate what the magnitudes of those forces are. But just based on the statics, the external loads, we would think, okay, maybe it breaks here, 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 or here. Those are the only places the forces are. But that's not what happens. And, you can visualize this pretty easily. We could do it right now. Here, someone give me your favorite pencil. It's actually going to break in here somewhere. And so we have to figure out kind of like what it means for something to like what's happening when something breaks. So something breaks at a point when the surrounding material can't supply the required loads to hold the body together. So what we want to do, instead of calculating where the outside things, what the loads are that the outside world applies to the body, is we want to figure out at every point what are the loads that the surrounding material has to apply to the body. So we want to calculate the loads applied to a point by the surrounding material. Okay, well, let's just start. I mean, really, you can think your way through how to do this for the most part. So let's start out with about as simple an example as you can come up with. So let's say we have a beam like this. You know, it might have joints and stuff, but let's say we've already done the statics to figure out what the loads are at the joints. And let's say there's 500 newtons down here, 500 down here, 1,000 here. So this is an equilibrium. And let's say that we want to calculate the internal loads here. Okay, and I'll give some dimensions. Let's say this is 0.25 meters. This is 0.25 meters. And this is 0.5 meter. And so what we want to do is calculate the loads applied to the left side of that red line by the right side. Okay, well, what I'm going to do is I'm going to isolate, instead of isolating this whole beam, I'm going to isolate the piece of it that goes all the way from the left end up to that red line. So I'll draw a free body diagram of the left part. That means we're ignoring all of this. Okay, so at the midpoint of the whole beam, there's 1,000 up there, there's 500 down there, but none of that is happening anymore onto the piece that we're isolating. this 500 down is still acting. But that's not all the loads acting on this thing. There's some stuff we're missing, and that's the key thing here. If you go around the boundary looking for the places where the surroundings contact our new object, the stuff in the light blue is applying loads to the part that we're isolating, okay? And so what kind of loads would those be? Well, think of what kind of, there's a joint. You can think of it as a joint between the left part that we're isolating and the stuff that we're ignoring. What kind of joint, what would you call that joint?
Like a weld.
Yeah, exactly. It's a fixed joint, weld joint, okay? And so what are the loads that a weld joint, a fixed joint applies to a body? We're in 2D.
X-line rotation.
Yeah, so 2 components of force and then a couple. And so that's all we're gonna do here. We're gonna say, okay, there's a component of force that way, a component of force that way. I'll call it Rx, Ry, and then there's a couple, I'll call it M. Okay, and now we'll go to Newton's second law. You could write out the full table for this, but we've talked about it before. It ends up being quite a bit quicker when you have horizontal, slender members to just do the calculations kind of as you go through. So for the X component, well, I'll write it out as full Newton's second law. So we have Rx, Ry, plus 0, negative 500 is equal to zeros. And then the moment equation, and I'm going to choose my about point to be here. So the moment equation says M, and then there's no moment produced by this Rx, right? Because the line of action goes right through the about point. There is a moment produced by Ry. So we have a plus or minus. What's the moment arm of that Ry?
0.25.
Yep, 0.25. So the moment arm is 0.25. The force is Ry. And is that a clockwise or counterclockwise rotation? Does that cause a clockwise or counterclockwise rotation around that about point?
Counterclockwise.
Counterclockwise, so this is positive. That's all the things that produce moments, so this is 0. And so what we get here is R is equal to 0, positive 500 newtons. And M is equal to negative 0.25 Ry. We already calculated Ry, so this is equal to negative 125 Newton meters. And then if you knew some stuff about that material, its strength and stuff, these loads would tell you whether you're concerned about that breaking at that spot along the beam. Okay? Yeah.
So then if a problem is asking us if something is going to break, is it then going to have a certain amount of torque or something we're going to have to look out for?
Yeah, so we won't do that in this class. We'll get closer to doing it in D form. The problem is the internal loads don't tell you anything about the geometry, and the strength of this thing depends on the geometry. So then the next level that you take is like, okay, well, we want to account for the geometry. So then you go to stresses and strains, and that's kind of what D form is all about. And then once you know the stresses and strains, then that's enough information to tell you, if you know stress and strain values for steel or whatever, to tell you whether that thing is going to break or how much it's going to deform or something like that.
So
But really, it's really in material science classes where you'll start to do that for actual materials.
okay.
Any other questions about? So this is the first pass through. This is kind of like the simplest form of it. There's one thing though. We're going to use a new sign convention. Like this works perfectly fine. You could do it this way, but we're going to use a new sign convention for those internal loads. Because we would like internal load values to be independent of how we calculate what's going on at that seam. Okay, and notice that I wrote the question this way, but we kind of arbitrarily said, let's figure out the loads applied to the left part by the right part. I could have just as reasonably asked, what are the loads applied to the right part by the left part? And notice that those are Newton's third law pairs. And so all of our answers, if I had asked that question, would be negative of what we have. Okay, so what we'd like is a sign convention where no matter how we calculate the internal loads at a spot, we get the same answers. Okay, so we want internal loads to be the same whether we calculate from the left or the right. Okay, so the sign convention that we're going to use is pretty arbitrary, but I guess in a way, like all sign conventions are just arbitrary. You just kind of agree to them. Is if we're working from the left, then we're looking at the point like this. The part that we're ignoring is this. And we're going to call a positive horizontal force this way. And we're going to call it T. So that's going to be the internal tension. We're going to call a positive vertical force down. Okay. Why? I don't know. But we're going to call that the shear force. And then a positive moment like this, couple, we're going to call M. That's the bending moment. So this one is called the tension. If you get a negative value of tension, then it's compression. This V is the shear force. And this M is the bending moment. If we were working from the other side, these would all be reversed. So if we're talking about the same spot on the same beam, now we'd be ignoring all the stuff over here. And our tension would be measured like this. Our shear force would be measured like this. And our bending moment would be like this. Okay, so depending on which side you're going from, the direction that you call positive is opposite. And the benefit of that is in either one of these cases, in the same problem, no matter which way you calculated it, you get the same values. Okay. So now you get the same values from either side. So let's just redo that problem, the one we just did, but with the new sign convention. So we have our body there. This is all the stuff that's part of the beam, but that we're ignoring. So we're ignoring this upward force of 1,000. We're ignoring this downward force of 500. We're including this downward force of 500. And now those loads that are applied by the fixed joint, we're going to write with this sort of funny new sign convention. We're going to call the horizontal component T, the vertical component V, and the couple M. So now Newton's second law says 0, negative 500, plus T 0.
Would it be positive 500? Shear goes down?
No, so each one of these, this all gets so confusing for everybody. But so what we're doing now is we're just going through and we're writing out all of these in vector form, you know, and we still have the usual coordinate system. It's just our sign conventions on our variables are new. The way to keep it straight, and this works always with vectors in free body diagrams and stuff, is think of the arrow as a unit vector, okay? And the number next to it is the number that you're multiplying to that unit vector. Okay, so for the 500, we have a unit vector of 0, negative 1. That's what the arrow says. Multiply it by 500 and you get 0, negative 500.
Sure. So it'd be 0, negative V?
Yes, that's the thing that's so like, that can mess you up. But if you think of that unit vector thing, you'll always get it right, okay? Unless you're stupid or something. So exactly, 0, negative V now. Does everyone follow what I'm talking about there? So it's a unit vector that you're multiplying by a value. And then this is equal to zeros. And so we get that the internal tension is equal to 0. The internal shear force is equal to negative 500. And then the moment equation, we're always going to use the left side as our about point. And so the 500 doesn't produce a moment. The M does. And you know that M is counterclockwise. That's why it's positive in the moment equation. This V, we got plus or minus moment arm times V. Always think of the direction of rotation based on the direction of the arrow. Okay, so if you have a force going down, it's going to cause a clockwise rotation around that red dot. Okay, And so here we're going to take the negative, and so we get m is equal to 0.25 times negative 500. And so m is equal to negative 125 Newton meters. Any questions about that? You with me on that? So what we've done now is, now if the free body diagram I'd drawn had been all the stuff in light blue, and I calculated those internal loads, I would have them drawn all in the opposite direction, and I'd get the same three values as I got here. I'd get 0, negative 500, negative 125. Okay? We're always going to do these calculations from the left side.
Why?
You know, there's no reason, but we're going to do it that way because you can always do it that way. And the more you do things the same way, the less likely you are to make dumb mistakes, you know. Okay. So these are the internal loads at the chosen spot on that beam, along the beam. All right, well, what we did here was, so that gave us internal loads at a single location. If we're trying to figure out how likely this thing is to break and where it's going to break, we want to do these calculations at every location. Well, numerically on a computer, the way you would do that is you would have the computer do these calculations at 1,000 locations or whatever, you know, and that's less than infinity, but enough to get a sense of what it's doing. But we can also, for these simple cases, come up with these internal loads as functions of x. So, so you could do it at 100 points and then fit a curve to your results. But what we're going to do is calculate internal loads as functions of x. So our tension is going to be like a function of x. Our shear force is going to be a function of x. And our bending moment is going to be a function of x. And so let's think about the example we just did. And let's say that, okay, so we have this beam that's like this, we have the 500 newtons down, 500 newtons down, 1,000 newtons up. Okay. And let's think about a free body diagram that goes from the left end to some arbitrary point this time, that's to the left of the 1,000 Newton force. Okay, so this time instead of saying that we're 0.25 meters from the end, we're going to say we're X meters from the end. Okay, the reason we can do this is because qualitatively, all of these, like whether your X was 0.01 meters or 0.2 meters or 0.24 meters or whatever, qualitatively that free body diagram would look the same. It would have a 500 Newton force and your internal loads. The only thing that would change is that X value. Okay, so so this time I'll draw this like this. We have the 500 Newton force. We have the internal loads. And this time our distance from the left end to the right end of our piece is X. Okay. So Newton's second law looks the same here. We have 0, negative 500 plus T0 plus 0, negative V is equal to zeros. So T is equal to 0 and V is equal to negative 500. So those forces didn't happen to change here. But now the moment equation we're doing our moment calculations around the left end. And so we have the couple that doesn't depend on a distance from an about point. But the V now, we have plus or minus a moment arm of X times this V. And it's minus because that arrow says it would be clockwise. And so this time our moment calculation says M is equal to V times whatever X you're interested in. That's our function of X. And we know what that V is. So M is equal to negative 500X. Okay, so now we have T, V, and M as functions of X, but only for X, you know, on the left endpoint. And actually, if you want to be really careful about it, which, you know, somewhat we're going to just kind of gloss over this fact, but we're considering X's in a range from just over 0 to just less than 0.5 meters. Everyone know that, seen that notation before? Everyone follow what I'm talking about there? So it can be 0.000001 X can be 0.0001, or it can be 0.4999999, or anywhere in between. What happens when it's 0 or 0.5 exactly is kind of a question. But we still haven't done anything, we still don't know anything about what's going to happen on the other half of the beam. So now we're going to take into account that the free body diagrams where the right end is more than 0.5 away from the left end, no matter what it is between 0.5 and 1, it's going to be qualitatively the same, and we can treat that all as a single free body. Okay. So now I'm going to do a free body diagram. It's still going to go all the way from the left end. We're always going to include the entire left end to whatever X point we're considering. What does this say? So from the left end to, again, it's an arbitrary point. Between 0.5 meters and 1 meter. So this time the free body diagram looks like this. We have the 500, because we're always going all the way from the left end. We have the upward force of 1,000. We haven't gotten to the other 500. And we have the internal loads T, V, and M. And this distance is what we're calling X this time. Any questions about that?
Are you picking the 1 meter just because it's easier math, or why not stop like just before the 500 on the other end?
Well, because what we're doing is we're trying to come up with a representation that represents everything from, we're not trying to do it at a single point anymore. We're trying to come up with a calculation that works for X equals 0.500001, and it also works for X equals 0.99999.
Okay.
So this picture is supposed to encapsulate all of those possibilities.
Since 0.1 is where the other 500
Right.
is, okay.
Yep.
Gotcha.
So we're taking into account all of the possible cuts like this where we have the 1,000 included, but we don't yet have the second 500 included. Okay. And so Newton's second law says 0, negative 500, plus 0, positive 1,000, plus T0, plus 0, negative V is equal to zeros. And so the internal tension is still 0. The shear force is positive 500 newtons. For that last calculation, we got the shear force was negative 500 newtons. And now we'll go to the moment equation. And I'll put my about point all the way at the left again. Okay, so the 500 doesn't produce a moment. The 1,000 does, though. Okay, so is that 1,000 gonna cause a clockwise or counterclockwise rotation around this about point? Counter, so this is gonna be a positive. What's the moment arm of that 1,000? 0.5, yep. And again, you can, if you want to, you could write out the tables for these. I don't think you'll want to do that eventually, but it works perfectly fine. And then we got plus m plus m. The v is always going to show up as minus vx because that arrow would cause a clockwise rotation. The moment arm is x, so this is just minus vx is equal to 0. And so we get m is equal to vx minus 500. Plug in the v that we've already calculated, and you get that m is equal to 500x minus 500. Okay, so what we have now is piecewise functions for these internal loads. T as a function of x is, so notice it was, well, it's 0 the whole way. That one's boring. But v was negative 500 for the x values between 0 and 0.5. And positive 500 for x values between 0.5 and 1. Is everyone following me on that? And then the bending moment as a function of x was negative 500x for x values between 0 and 0.5. And 500x minus 500 for x values between 0.5 and 1. And you can graph these out to visualize what's going on. So t, that's just 0 the whole way. V, that one was negative 500 for the first half, positive 500 for the second half, and we're just going to draw this as a vertical line. There's actually a reason that we're going to do this in math class. They would go crazy about doing that, obviously. But remember that we're treating these things as point forces that are really spread out over some possibly microscopic, but it definitely spread out over some range. And so the more that point force is spread out, the more that line would be at an angle. Okay, and so we're kind of just approximating what's happening. We're saying we don't really know. We haven't done the detailed work to figure out what's happening inside of there, but it's basically just quickly going from this negative 500 to this 500. And then the bending moment goes down to a value of negative 250. and then up from there to 0. Okay, so looking at this, you kind of have an idea that if the geometry, the cross-sectional geometry is the same for this member over the whole length, like where are you most concerned about this breaking? Well, the story is pretty much the same due to tension and shear force over the whole thing. That's because shear force, positive and negative, don't really make any kind of important difference. So basically, except right underneath that load, we have a magnitude of 500 newtons of shear force everywhere. The only thing that changes for an internal load is that as you get closer to that center line, you get a bigger and bigger magnitude of bending moment. And so as you get close to that point force in the middle, you're more concerned about this beam breaking. That's sort of the idea of internal loads. Okay. So where do you have to, notice that we did this with 2 free body diagrams. Where do you have to switch your free body diagrams? So where do, what these are called is subfunctions. I don't know if you remember that, but these 2 different functions in the piecewise function are called subfunctions. Where do the subfunctions change? Yep, so anytime you have a point force, you have to go to a new free body diagram. Anytime you have a point couple, that would be like a place where a motor is attached to this thing that's applying a torque. And that we haven't gotten to this yet, but you have to deal with a new subfunction when a distributed load function changes. Okay. Any questions about that? I'm going to give you a problem or 2 to try to work through on these. And if you can't do them, that's fine. If you have trouble with them, bring your questions to class and we'll go through them on Wednesday. And we're just going to do a few examples next time. Okay, that's all.